In this video, I will show you several examples of how researchers use difference in difference analysis. I will start with an event study design by Lafortune et al. That was published in the AJ Applied in 2018. And to me, this is a fantastic example of a diff-in-diff paper. It's extremely well carried out. It is very transparent in the way it describes the data, it graphs the main results, and also in explaining what different types of diff-in-diff effects they actually identify. And what is particularly nice is that they typically identify 3 different diff-in-diff effects, and for each of them they explain exactly what that diff-in-diff effect actually is and how it can be understood. Now, what they study there is a gradual reform in the US in terms of school when it comes to school finances. So for public schools, you obviously have huge heterogeneity in school finances because the school finances depend, among other things, on local tax rates and local tax revenues, which are obviously higher in places where people with higher incomes live. And there was a gradual change in the US when it comes to the state support for public schools. So in the 1980s, the principle was that school funding was equity-based. So the idea was that all students get the same regardless of the type of school it is, the type of neighborhood, the type of need. Later, what they decided on was gradually the different states in different years switched to so-called adequacy rules, whereby basically schools with weaker students would receive more support, and in the hope to equalize that initial disadvantage that students in those schools would have. And what they do is they use a difference in difference design to look at this gradual rollout of this switch from equity-based to adequacy-based school funding. Yeah, so it's a classic event study design. There was 64 reforms in 26 states. So there was some states that had multiple reforms in multiple years, and you have to read the paper to think about exactly, or to read about how they dealt with the fact that there was multiple reforms in one state. They typically use the last one, but it depends on the type of reform it was. And so this follows very clearly a difference in difference logic. So you had some states that were never treated at all, some states that were treated very early, that switched very early, and others that switched late. And then they use an event window around that time to look at, well, what is the effect of switching on test scores. And obviously for each state, they want to use their estimator to have a counterfactual, as in what is you can only interpret the effect as causal when you have a counterfactual that is test scores in that state had they not switched to adequacy-based school funding. So the identification assumptions that they're making is that in absence of the reform, test scores would have been the same in states with and without the reform. What they also explicitly state, even though it's not a critical assumption for difference in difference, it's good to have, it's very important to have, but it's not a must, is that the timing of the reform, they claim, is as good as random. So whether a state had that reform early or late is as good as random and depended simply on some delays in court cases, and so there is no difference, so they claim, between states that would have adopted that policy early and those that would have adopted it late. Now, what they do in the first instance is they have a very simple event study design where they look at the outcome for students who are in state S at time t, and they have, again, a two-way fixed effect model here. So they have state and year fixed effects. And then they have an indicator for basically whether you're in a treated state after the treatment, and that would then give them that diff and diff estimator beta. And so here it's called beta jump, and why it's called beta jump we will see in a few slides, because it basically just tells you when you think about a different diff design. So you have at some point the state gets treated, and then you have that jump in test scores, and that's what they're really after here. Right, so what they also do is they have a useful parametric extension, and then they also use a flexible model. So where you have time dummies, so dummies for each period within the event window. So what they do here is they split the sample period, so the event window, into 3 periods. One is the phase-in region, that is basically the lead up to the event. Then they have that they account for the jump, and then they also account for trends after the event has passed. So to think about this, if you think about the first model imposes basically does not impose any state-specific trend here. So the idea of the first model is basically, if I graph this at the bottom, is that you have an average before, and then you have a jump, and then you have an average thereafter. And the size of the jump is basically the effect you're after, right? So if the jump is 0, then there is no effect. If the jump is positive, then there is a positive effect, or if negative, there is a negative effect. What they do in the second design is a little bit more sophisticated, whereby they allow for a state-specific trend before. That's what you can see here. And then also a state-specific trend after that can be different from the one before. Right? So they allow basically for a trend break at the time of treatment, and then they're still interested in the size of this jump. Okay? So to what extent do test scores increase when we switch from equity-based to adequacy-based school finance? So these are still parametric event study designs, because you know all you're estimating here is this one average parameter, but you have no flexibility. You force basically anything that comes afterwards as being treated, anything before as being untreated, but no difference between different periods post or before treatment. So what they do then is also to use a more flexible, basically a non or semi-parametric event study model, whereby they have for each year in the event window, so a couple of leads, a couple of lags, they have a dummy that equals 1 if we are after the event in a state that has been treated, and 0 otherwise. And so obviously then the states that have been treated very early on, that dummy is 0 for up until they're treated, and then jumps to 1 for all subsequent periods. And states that are treated late, that is 0 most of the time, and then it jumps to 1 eventually. And so then for each of those periods within the event window, again, they get a different coefficient, which they then plot together with the standard error. Now, there are advantages and disadvantages to all those models. Why would you not use the most flexible model? Well, because it's obviously quite taxing on the data, right? Because you need to, instead of estimating one parameter, and you have a certain number of degrees of freedom here to estimate that, because you already use up some degrees of freedom with those fixed effects. But you would, in the this model you would estimate 3 parameters. In this model you would estimate 1 parameter. But in that flexible model you would obviously estimate however many periods you have in your event window. So these can be a lot more than 3 parameters. So the statistical power you have to precisely estimate any of those parameters is obviously limited by your sample size. On the other hand, if you have a flexible model, that's obviously more informative also about dynamic adjustments to those policy changes, and that's why people like them so much. Plus, you're not forcing the pre periods, so the leads, to follow the same trend, which is what you do if you have just a post dummy, but you can actually look at whether there is any gaps or any significant pre-trends which you can use as a diagnostic test. And the reason why I like this paper so much is because they plot those two models, or the results for those two models, in the same graph. And so what you can see here is, on the one hand, these lines that are a little bit more jumpy. That's the coefficients and 95% confidence intervals from those flexible diff and diff coefficients, so from that flexible diff and diff model. And then the dashed line, it's not shown here with confidence intervals, but you could obviously construct them here as well. It would just get a bit messy on the graph. And the dashed line is simply the parametric model. Okay, so where you force the effect after the event to be constant. Okay, and then obviously you're just interested in the size of the jump. And what you can see here is that the effect is that there is an effect. So they look at the lowest 20% in terms of prior test scores. And then what they look at is the effect, first of all, of that reform on school finances. So this is basically what one would call the first stage, right? So that reform comes in, then they want to first see, is there an actual effect on school finances? And they find that at least 10 years after the reform kicks in a state, there is a positive effect. So that state sees a disproportionate increase in school finances in the bottom quintile, which is where you would expect it to happen. That's also for practical purposes very important. If you do work like that, where you look at the effect of a policy on outcomes, it's always good to give us some idea of a first stage, whereby you first show us what is the effect of the policy on what the policy actually intends to do, right? Whether it's school finances, family incomes, whatever. And then you look at the longer run outcomes, because that makes it a lot more credible. Okay? So here they show the results the same for the highest 20%, and there is no difference. Okay? And then they show that it also has an effect on actual test scores. I'm not showing these here, but that's what they also show. Okay? So one thing that's important here, also what I like in this paper, is they show their results graphically, and then they show their results in tables. Now the results from those flexible models, showing them in tables is really a waste of space. They're best shown graphically, and if you see a graph like that, you can say, yeah, okay, that makes sense. There is no significant pre-trends, and then once the reform kicks in, there is this disproportionate increase in states where that reform happened relative to other states. And so yeah, I would recommend that you do both. And also what I like here as well is that they, in the same graph, show the parametric and the non-parametric model, which is quite nice, okay? Because the non-parametric model, for power reasons, can sometimes be a little bit hard to interpret. But then when you see the parametric estimates that they go in the same direction, then that's very, very helpful. Now, when you run any difference in difference design, you need to bring supporting evidence for the identification assumption. And that doesn't only hold for the difference in difference design. For any causal inference, whether it's through an experiment or through IV, RD, difference in difference synthetic controls, whatever you use, you always need to justify why your identification assumptions are valid. So you need to state them in your paper, and you would not believe how few authors actually do that and are so transparent to state them. They kind of just hand-wavingly talk about parallel trends without actually telling us what they actually mean by that. And then you need to justify why they hold. And so in different designs, the commonly used diagnostic tests are parallel pre-trends, right? So you've seen this here in this picture or here, where you have no significant difference before, and from that the authors the authors use that as a justification to say, well, then it's plausible to assume that these trends would have also moved the same way without the treatment afterwards. But that is obviously a strong and untestable assumption. The way we use this nowadays is actually the other way around, to say, well, if there are significant differences before, it's very hard to justify why there wouldn't be any differences at all afterwards. Okay, but parallel pre-trends before are obviously not a proof for parallel pre-trends or for parallel trends after the treatment has been given, which is where you actually need them. Right? Another thing that is very, very important to do in any study is to run placebo tests. Okay, so you basically run the same model, but you use units that are plausibly unaffected by the treatment. And if you then find significant results that are similar to what you're doing in your own work or in your what you're getting out of your main result, then this means that your estimator probably picks up something else that you're not aware of. But it's hard then to justify a causal interpretation. And one type of definitive estimator that actually incorporates that idea of units that are plausibly unaffected by treatment is the triple difference design. Right? So instead of having double differences, before, after, treated versus non-treated, you now have triple differences. But what is that? Let's go back to the minimum wage example. So what you do here is the third difference is, it's basically a meta difference. It's the difference between two difference in difference estimates. So you do your different diff analysis for the group where you expect the effect to be there, and you do the same analysis for a group where you do not expect the effect to be there. And then take the difference between those two estimates. Right? And the advantage of that is that you can difference out a lot of time or period specific or unit specific shocks there. Example. In the minimum wage example, it would be that you have New Jersey and Pennsylvania before and after. That's the Kruger case. But we could also take an additional control group, which are plausibly unaffected workers by a minimum wage change, right? So if you take, for example, workers with a college degree, they're probably not so affected by a minimum wage change, under assumptions about complementarity, blah. But for the moment, let's assume they are not. Okay, and so what I do basically is I compare now fast food workers relative to college educated workers. So I compare the employment of fast food workers relative to college educated workers before and after the introduction of the minimum wage in Pennsylvania relative to New Jersey. So how would I do this? I simply add a third dummy and a third interaction, or a triple interaction. Okay, so you have here now a model with fixed effects for periods, fixed effects for whether a unit is treated, and in the minimum wage case, treated means the unit is in New Jersey after the introduction of the minimum wage. Even if you're a college educated worker in New Jersey after 1992, you would still be counted as treated, even though the policy doesn't do anything for you. Okay, it's just, you know, being in the right place at the right time. That's what treated means here. And then you have a third dummy here that's new. That's for whether you are in the group where the treatment actually works or whether you are in the placebo group. Okay, so this is basically treated versus placebo group. Then we have a couple of two-way interactions which we need to have in order to ascribe an actual interpretation to that triple difference term here. Okay, so what we compare now is fast food workers in those two states before and after the change relative to the same change in an unaffected group. That's what a triple difference estimator does. Now you can already see by me, you know, listing those differences, it's getting harder to interpret, which is why you always have to exercise caution when using triple differences. And typically the way people do it is they first show the double differences and then they say, okay, you may be worried about state-specific shocks. You know, there may be some violation of parallel trends because, you know, employment in New Jersey dropped by a lot more and would have dropped even without the minimum wage. And so therefore I use another control group that basically captures that additional drop in New Jersey relative to Pennsylvania. And then if you do it like that, you first show your 2x2 model and then you show your triple difference. That usually works. If you only use a triple difference model, you have to offer a reader a lot of guidance. A paper that does that in a fantastic way is this one by Cortez and Pan on the effects of domestic outsourcing on female labor supply. So what they're looking at is at the effect basically of immigration, of low-skilled immigration on female labor supply. And so what they look at is there was a policy in Hong Kong in the 1970s that was specifically targeted at recruiting so-called foreign domestic workers, so people who come and work in the household, who mainly came from the Philippines and Thailand. And now you have this issue that, you know, Hong Kong is a very small state, or very much a city with a bit of surroundings. There is no obvious control state. So what they do here in the study is they use Taiwan as a control country. But that's still, you know, when you think about it, is Taiwan really a good control? Well, they didn't have that policy. Yeah, it's in Southeast Asia. Is that really a good control? But that's where triple differences come in, really, right? Because what they do is they compare then people who would be in need of a foreign domestic worker, namely those with small children, to people who are less in need of a foreign domestic worker, those with older children of school age where the children are looked after during the day. And so they compare then the female labor supply trends in Hong Kong and Taiwan over time of women who have school-age children versus women who don't have school-age children. And so that makes obviously the two places a lot more comparable relative to just a double difference model. It's not perfect, but it does work, and they do a very good job at justifying it. Okay, so here they just show some descriptive statistics You can see here basically that the time series with the triangles is that the wage of foreign domestic workers has become a lot lower relative to other wages, as in it has become a lot cheaper over time to hire a foreign domestic worker in Hong Kong. And you can also see here that especially among women with a higher education, the share of those hiring at foreign domestic workers has gone up a lot. So that's the time series here at the top. And even among those with a medium education, it has gone up. And so again here they look at then the triple differences. So they compare women with and without school-age children before and after the reform, and they do the same for Hong Kong, and then have Taiwan, where they do the same difference in difference analysis as a placebo, and then they take the difference between Hong Kong and Taiwan in those difference in differences. So you can see the results here in this graph. So they basically have the pre-period where you can actually see that that female labor supply in Hong Kong among women with school-age children was actually lower compared to Taiwan. But then you see in years afterwards for that triple interaction that it actually reversed, that relative to the same share in Taiwan, there was a disproportionate increase in Hong Kong of in labor supply among women with school-age children. And then that, along with other evidence that they bring in the paper, they interpret as the causal effect of that recruitment policy on, or of foreign domestic worker use or employment in the household on female labor supply. Right? So triple differences is, if you do different diff, always an ace you should have up your sleeve and that you should think about. But once again, I do not advise that you use it as the main result unless you do such a good job as Cortez and Pan. So if you manage to do this in a convincing way that others immediately understand what you're doing, well then by all means do it. But otherwise, it's typically used more as a robustness test to say, look, you may still be worried in my 2x2 or in my whatever, short diff in diff. You may be worried about the parallel trends assumption being violated. Now I'm using an additional control group that is plausibly unaffected by the treatment, and but that helps me to difference out any sort of unit-specific time trends or unit-specific shocks. But the other thing you should notice is that I do not see a way of having a triple difference design for a staggered adoption design. So those classic diff in diffs where you have a rollout of a policy over many states in many years, I do not see a triple differences working there. I mean, unless you see an application that works somewhere, I don't think that works. So to wrap up in this video, what we've seen are two very good examples of difference in differences studies. One being an example for a combination of parametric and non-parametric difference in difference methods, in that case event studies, also with staggered adoption. The other being a triple difference design. Once again, when you run a difference in difference study yourself, you obviously have to justify the identification assumption, state it, justify it, or if there are multiple assumptions, state them. But then also pick a paper that's really good and model your study after it. And then afterwards, look at the latest literature and look at the methodological refinements. And you may have to do some additional tests or provide some additional guidance to readers that authors in papers that were published 5 or 10 years ago we're not forced to do. And that's simply because the literature has moved on since, and you obviously need to stay up to date if you plan on doing this type of work for the next however many years or even decades.